So far, we have used circuits to see basic operation of operational amplifier and a transistor, MOS-based transistor. The computing machines today are everywhere, and all of them use digital computing. First, we were using bipolar junction transistor, but now we use mostly NMOS and NMOS and CMOS, which means we also have PMOS as well. So what we are getting into is we are going to study the fundamentals of digital integrated circuit design, the basic components of a CMOS circuit, inverter and logic gates. Because CMOS is in 98% of newly digital systems. We will look at how we use NMOS and PMOS transistors as the building blocks of the logic devices. There are a bunch of logic functions that need to be done where we either just have to invert a signal, maybe we have to use it together with a number of other mathematical operations. In all those cases, we would be looking at what is the arrangement of transistors as voltage controlled devices, voltage controlled switches, because switching is one of the fundamental operations in addition to amplification. So we'll see at how we synthesize, how we create CMOS logic circuits that can do those fundamental logic operations and implement what we call Boolean functions. So let's take a look at an example from chapter 4 where we were introduced with diodes, their forward bias and reverse bias. And this is a question which was looking at there is a low value, high value, depending on the forward bias or reverse bias of a diode. And using that information, how can we find out what would be the voltage at X or Y? So in this case, we are going to use A and B as the inputs, and we'll have two levels of A and B, high voltage for 1 and low voltage for 0. And what we get with this input and output, we call that as truth table. So the logic function would define what we get. So if we make a table, so that's going to be with A, B, X, and Y. So the left one is what you would call as X. We have to see that in this circuit there is a power supply and we are getting some current. These two, if they are at low voltage, that would mean that if either of one is low voltage, these both will be forward bias, so the current will flow this way. So the end result is that you would get the whole signal going there and we will not get anything here. So which means if they both are 0, X would be 0. If any one of turns 1, even then the other one will be conducting. So one of those. So if we take A is equal to 0, B is equal to 1, so this may be cut off, but still signal is going through D1 and X would be still a 0. Similar way, if we take A to be 1 and B to be 0, signal is still going through and X will be 0. For this to be at high value, they both have to be high value, and in this case, both diodes will be reverse biased, so hence signal will be available at X. So in this case, the output would be 1. And now if you look at the Y, for the Y, when any of these is forward bias, you will get a signal here. But if they both are reverse biased, there will be no signal at Y. So there will be no signal flowing through to this power supply. So in this case now, if you look at it, when both are reverse bias, there is 0 output. But if any of them is forward bias, you get a signal at Y. And of course, if they both are forward bias, you get a signal at Y. So this situation can be described, if I were to write X, I can write that to be a product of A and B, which means if any one of those is 0, the outcome would be 0. So A and B both have to be 1 to get an outcome. So this is an AND gate. Now if I look at Y, how do I define Y? If any of them is 1, the outcome would be 1. So which means either A or B have to be 1. Now this is then what you call as OR gate. The question keeps further that what happens if A and B are equal? So that would mean X and Y would be the same for if A and B are equal. So which is these cases, right? And then it says if they are opposite, which is 0, 1 or 1, 0, that means they will be opposite. So X will be opposite than Y. So that was what we have done so far using diodes and seeing that how would diodes play about the voltage drop and what happens to that voltage across the device. Now looking at this basic circuit, we can look forward and we can see that this is diode and the same circuit can be implemented with a transistor. Now in the case of transistor, the very fundamental operation would be where transistor would be switched on and off. So we have seen that we use gate between source and drain. So the gate, when this is turned on, provides appropriate voltage depending NMOS, PMOS, doesn't matter. The signal will go through and you will get a 1 at the output, high voltage, right, signal at the output. But if this is turned off, we will not get a signal at the output. So in a way we can see that high and low level of voltages can be achieved by turning the switch on and off through the gate voltage. So we are operating this transistor either in the on position, triode region, or in the cutoff region, which would be off position. So specifically, if you think about it, NMOS transistor behaves like a closed switch. When its gate value is, so if I take this as a switch, so this behaves as a switch between source and drain depending on whatever is the gate voltage. And when it is closed, there is a small resistance, what we call RDS, and we calculated that what would be the RDS. Now, and this gate voltage has to be more than the threshold voltage, and we call it overdrive. And then we took it further, that how we can uh, turn the drain to source voltage higher than overdrive voltage to get to saturation. But here we are just using it as a switch, which means that when the gate voltage is high, the power supply level, whatever has been applied, would go through, and we will get a high voltage on the other end. Now, on the other hand, if the gate voltage is low, which would mean that now this switch would be open, so which means that there will be no voltage on the output, and we would get what you call as zero, logic zero, low voltage. So this was for NMOS. If you are using PMOS, that would be the complementary operation than this. So in that case, to turn the transistor on, the gate voltage is made low, and raising the gate voltage to the VDD would turn the PMOS transistor off. And this is what we can see in this figure. So just an open switch or a closed switch, transistor which is controlled by gate voltage, and in this case gate voltage is shown as VI, input voltage, because then that's resulting into voltage seen at the output, and that's also shown in the form of a bipolar junction transistor. This would be the case when an inverter operating with power supply V plus and 0 on the ground can be implemented using these situations. So this is just the op amp that we have seen before, and that also operates in a way where our output would be controlled by input. Now, let's take a look at the basics of logic before we get into making circuit to implement that logic. There are three basic logic gates, and then there is a inverter used with them. So inverter is something that would just flip the input into opposite. So if there is 1 at the input, you'll get 0 at the output. If there is 0, you'll get 1 at the output. Or is the operation that we just saw, that any one of the inputs is high, any one of the input, if they're high, it doesn't matter A or B, or both, the output would be high. Or AND gate, that for the output to be high, both of them have to be high. So these are the physical model or physical way how do we show the Boolean function without looking at the circuit inside. But that's the goal. We want to look at the circuit inside. So what we do is, with these we provide logical operations on the inputs and produce a single logical output. Now if we place an inverter at the output, what we are getting is, we are getting the inverted output of what a regular, just a good old OR would do, or good old AND would do. So we are flipping that or inverting that, and that bar is just depicting that the input is being converted or changed. And this information leads to what we uh, call digital binary logic. And in digital binary logic, we would be writing circuits, or we'll be doing digital electronics. And we'll see the signals in discrete band of levels of 0 and 1, which would be indicator of what's the analog level. So instead of having a signal, continuous signal in analog, a series of ones and zeros would be what would represent that signal. So that's analog to digital, and digital electronics helps us do that. So all these levels would be then represented by combination of these in high level or low level. So if you think about it, our op amp or transistor are analog devices, right? So we saw they have triode region behavior, or for diode we have the breakdown, forward bias and reverse bias. So there will be some effect of tolerances of these analog devices in getting these zeros and ones, or noise even. And that would be something we'll look that from what we have done so far when we are using it for digital logic, what are the issues and what are the things that we need to know. So positive or negative or 0 and 1, that's just going to be relative in our circuits, but now we'll have to think it in terms of high and low. So we have these elements which would give a specific outcome depending on their operation, and we write them as truth tables. So inverter is just 0 goes, inverter of 0 is 1, and inverter of 1 is 0. And similar way, OR and AND is what we just saw. And we can, so this is now separate truth table for OR and AND. And then we have NOR. Now you have to see something. As the name implies, the output is just flipped from going from OR to NOR. And in similar way, when we go to from AND to NAND, again those outputs are flipped. So if you know the basic truth table, the advanced truth table, or a circuit which has bunch of parts to it, we should be able to see how the signal is going to change, or what would be the signal value that will be seen at the output. And then we have whole digital logic algebra, which helps us identify some basic rules which can be implemented using our circuit. So we take the union, which is or you take intersection. So set theory, if you take intersection, which is and that has what you call associative properties to that. So that if you take union and you take the inversion, is the same that you would take intersection of the inverted inputs. So that's just basics of Boolean algebra. Now, we saw how we can implement that. So let's just see if there are two diodes, what happens. And these are just some voltages that are shown. You are using 5 volt, there is 0.6 voltage drop. so there's 4.4 voltage drop across a diode. So what you're left with is the voltage from this, whatever is left over, and this voltage will then define what do we get here. We get high or low. So, and these are shown as open, but depending on whatever situation we are looking at, we can close one, leave other open. We can close this guy and leave this open. So in both cases, we can see if both voltages are zero, they both will be forward biased, both will conduct. So the output would be low because the voltage drop is happening across diode. And if one of them is made reverse biased, so we get one diode, B diode becomes reverse biased, does not conduct, but the A diode is forward biased and conducts. So we see these situations which we already saw how we would write them in a truth table. Similar way, OR gate, if both are reverse biased, they do not conduct, the output is low. And if any one of them conducts, we get high voltage at the output. And that's again, these two switches can be thought of like these guys to be forward bias and reverse bias, and their subsequent results that come from them. And there are other operations where we can take a gate and we can convert it through one device and still get back our signal. So the simple diode logic is showing AND and OR, but not inverter. So, but those can be achieved by using other applications. So like shown here. So to build a functionally complete logic system, then transistors are used, and the inverter is the most fundamental building block. So here what we are showing is if you want to achieve this, there are equivalent ways how you can achieve that in other forms as well. So it's instructive to see that what's the depth that we would be dealing maybe in an advanced course. But here we'll just look at its circuit application, circuit implementation, that how we can get that result of specific logic operation. Now, diode is the basic thing that we use. So here we are seeing digital inverter where the transfer characteristics are supposed to be when there is high input, we get low output. We have low input, we get high output. And these levels of V plus and V minus would be then the power supplies, and the signal has to stay within those. So that's what we studied in diode transfer characteristics, that there is the signal gets flatlined if it goes close to the power supply. And VH and VL are then what would define the high and low in a device. So we have to know the voltage transfer characteristics of these devices when we are looking at implementation of those circuits.